Hello and welcome to a new episode on the Basic Mathematics series. In the previous episodes, we were talking about integers, positive and negatives, natural numbers, additions, subtractions, multiplications, and divisions in those realms. In this video, I want to focus on a very fundamental realm for algebra and mathematics, rational numbers. In a nutshell, a rational number is any number that can be expressed as a fraction. So if we have something like AB, it's a rational number, but it has to comply with certain rules. For example, A and B have to be whole numbers or integers, and B, or the denominator, has to be different than 0, right? Rational numbers can be expressed as fractions or as decimals, right? This is the same as expressing this. They have different variations, let's say. So, for example, any integer can be expressed as a rational number. Let's say we have 2. This is the same as expressing like 4 over 2 or 8 over 4 and so on, right? We can also have periodic decimals. For example, 1/3 can be expressed as 3, right? So rational numbers are numbers expressed as fractions where A and B are integers and the denominator is different to 0. They are finite or periodic when expressed in decimals. This expressed in mathematical language could be Q. This is a letter that we usually use for referring to rational numbers. And we can say where A and B, such that A and B are part of the integers realm and B is different than 0. Now let's talk additions. In the previous videos, we've seen some properties of additions, like they are associative, they are commutative, they are distributive, and these same properties apply here for rational numbers. The only thing that we have to keep in mind is that when we try to add two rational numbers, for example, A over B plus C over D, we have to find a common denominator. So we can do that by multiplying the denominators, right? Like doing B times D, and then we can associate this like so, plus C times B. And by distributivity, we could express it AD plus CB over BD, right? If we wanted to have this as numbers, for example, we could do 2 over 4 plus 3 over 6, and we can do the same. Find a common denominator, 4 times 6, and this will be 2 times 6 plus 3 times 4, and there we go. We have 12 times 12 over 24. And this is totally fine, but if we wanted to take it to its lowest expression, this would be 1, or just 1 over 1, or you could express it 2 over 2. Again, rational numbers can be expressed a lot of different ways. These same rules apply for positive and negative numbers. When we have negative numbers in rational numbers, we would have, for example, minus A over B is the same as saying minus A over B. And this is the same as A over minus B. Now, for multiplications, it is simpler in my opinion. So if we have something like A over B times C over D, the only thing that we have to do is multiply denominators and numerators. So we will multiply the denominators B times D and the numerators A times C. So this is AC over BD, right? Same here. If we wanted to have some example, let's say 4 over 8 times 3 over 7, for example, right? And this could be 4 times 3 over 8 times 7, which would give us 12 over 56. And if we wanted to take this to its lowest form, it would be 6 over 28, 3 over 14. And this would be the lowest expression. Now there's another way I would suggest you could look at this. For example, we can use the rules that we've seen before. If we have something like 4 times 3 and 8 times 7, we can also express this as 4 times 3, we can do the same, and here we could do 2 times 4 times 7, right? And this is the same thing. So here we can do 4 over 4 is 1, so we can substitute this 1 times 3 over 1 times 2 times 7. And maybe this is an easier way of achieving the result, right? Before making the multiplication and all of that, you can see how you can make your life simpler by finding this sort of expressions. For divisions, we do what is called like the cross multiplication. So for example, we have A over B divided by C over D. This you can think of like cross multiplying. A times D, AD, or B, C. And the reason for this is because if you do it like this, you're good to go. But I like to explain why this happens, and also I think it's simpler to understand it as the division being an inverse multiplication, right? So what is an inverse multiplication? If we have 1 over 3, the inverse multiplier of 1 over 3 would be 3 over 1. Why? Because if you multiply 1 over 3 times 3 over 1, you get 1, right? Or this is 3 times 1 over 3 times 1. So a division, you can think of it as the inverse multiplication of the denominator. So when we have A over B divided by C over D, you can think of this as being equivalent of A over B times the inverse multiplicator of C over D, which is D over C, right? And then follow the same rules as multiplication, and you get the same result. Previously, I mentioned that rational number needs to be periodic or finite when expressed in decimals, right? The reason for this, I want to make a quick exercise. Imagine we are asked to find the number which is a square root of 2. For example, a way to look at this is if we do 1 squared, we will get 1. If we do 2 squared, we will get 4. So we know that the number lies between 1 and 2, right? So let's say we tried something like 1.5 squared is 225. So we know that the number is between 1 and 1.5, right? This is thinking kind of like a program. You could program this to search for that number, no? And then you know it is lower than 1.5 and bigger than 1. So let's try 1.2 squared, and this would be 144. So now you know it's between 1.2 and 1.5. We can do 1.4, for example, and this would be 1.96. So now we know it's between 1.4 and 1.5, right? So we will try 1.45, for example, and 1.45 is 2.1. So we're over that. So now the number lies between 1.4 and 1.45. And you see the point here, right? You will keep adding decimals to this, and this will be added to infinity. That means that this number cannot be represented as something like A over B. We can prove that the square root of 2 is not a rational number Because if it were a rational number, it would be something like this. It means square root of 2 can be expressed as the fraction of a over b, right? Where, of course, a and b are integers, and b is different than 0. Remember that? We saw that in the first exercise. Right. So we can test this by just rearranging things here a little bit. We have square root of 2 is a over b, right? So this means that 2 can be expressed as a squared over b squared. And this means that 2b squared is equal to a squared, right? B squared. So at this point we can see that a squared is a pair number, right? Because it is something multiplied by 2. So we can express a as 2k, because the square root of a pair number is also a pair number. So in this case we could substitute, right? 2b squared, we can express it as 2k squared, right? This is the same thing. All of this is the same expression. And we can actually express it like 2b squared equals to 4k squared, right? And we can divide both sides by 2, and we will end up with b squared equals 2k squared. So apparently b squared is also a pair number, or b is also a pair number, and this is where we find the contradiction, right? Because at this stage we need this to be two integers in its lowest expression, which means that they do not have any common denominator at this point. And in this case, if we do all of this process, we can see that both of them have a common denominator, which would be 2. So this is what is known as a proof by contradiction, and square root of 2 is not a rational number. So to finish off, I would like to make a simple exercise so we can, consolidate all of this knowledge. So let's say let a be a rational number m over n different to 0. So that means m, I cannot write here, m is different to 0 and n is different to 0, right? Our job is to prove that there exists a number b such that a times b is b times a, and it is 1. We've actually done this before. We will see what we're talking about here. We know that a is m over n, right? We can also imagine that we have the number b like n over m. This sound familiar? If you notice, this is basically the inverse multiplication. So we can express a times b as m over n times n over m, which will give us m n over n m by distributivity m n over m n, and this is basically 1. And here is our proof. And again, this is nothing but the inverse multiplication. If we did this with numbers, for example, let's say we have 3 over 2, there exists a number such that multiplied by this will give us 1. Which is it? Well, the inverse multiplicator, 2 over 3, which would be 6 over 6, which would make it 1.